For decades, the Turing Test stood as the historical gold standard of AI evaluation, a simple conversational assessment designed to see if a machine could pass as human. Recent large language models, like ChatGPT-4, have successfully passed rigorous, modern iterations of this exact test. Passing this conversational threshold triggered intense industry interest. It led directly to claims that these models are sentient, or that they are rapidly approaching artificial general intelligence. Artificial General Intelligence, or AGI, refers to a theoretical system capable of understanding, learning, and applying knowledge across any domain at a human level. This chart tracks the performance of large language models on the MMLU, or Massive Multitask Language Understanding Benchmark. MMLU is a suite of 57 subjects across STEM, the humanities, and more, designed to test general knowledge. Recent models have climbed past the 90% saturation mark on these exams. When a metric reaches the top of the curve, it stops being a useful measurement. This statistical saturation renders traditional academic tests obsolete for judging true artificial intelligence. The models have effectively memorized the common patterns found in human test banks. There is a gap between conversational fluency and actual cognitive reasoning. Tech professionals routinely equate the two, assuming that because a machine speaks well, it must think well. Mastering human-like text generation creates a convincing illusion of understanding. Behind that prose, however, is a deficit in actual cognitive synthesis. In 2026, researchers responded to this benchmark saturation by creating Humanity's Last Exam. It is a scientific assessment designed specifically to test actual expert-level knowledge, rather than standardized trivia. This bar chart displays the baseline scores of the most advanced AI models on Humanity's Last Exam. The scores are extremely low. GPT-4o scored 2.7%. Claude 3.5 Sonnet managed 4.1%. OpenAI's o1 model reached 8%. Even the absolute cutting-edge systems like Gemini 3.1 Pro and Claude Opus 4.6 hit a rigid ceiling. Their accuracy stalls between 40 and 50%. We have systems that score above 90% on academic memorization, yet fail to break 50% when required to synthesize complex, expert-level information. To map the actual frontier of machine intelligence, evaluations must move away from conversational imitation. The tests must focus on deep, context-dependent expertise. The root of this evaluation problem dates back to 1950, with Alan Turing and his foundational paper, Computing Machinery and Intelligence. Turing deliberately bypassed the abstract question, can machines think? Instead, he proposed a functional behavioral test. He called it the Imitation Game. Player A, a machine, and player B, a human, are isolated in separate rooms. Both send written responses to player C, the human interrogator. The machine wins by successfully tricking the interrogator. The goal is deception through text. At the time, computing hardware consisted of massive, wire-heavy racks like the early Manchester computer. Proposing that a discrete-state machine could possess intelligence was a significant conceptual leap. Turing realized that a universal digital computer, equipped with enough storage, could theoretically mimic the behavior of any finite system. He designed a test for functional indistinguishability based entirely on written output. By doing so, he created a target that could be beaten by statistical probability rather than actual reasoning. The strict limitation to written language is the critical vulnerability in the Imitation Game's design. Early chatbots from the 1960s and 70s, like Eliza and Perry, exploited this loophole. They used simple keyword matching and deflected questions with psychological responses to fool judges. Modern artificial intelligence solves this exact same language problem by calculating statistical weights across trillions of distinct parameters. Today's large language models rely on transformer architectures. A transformer is a deep learning model that processes sequential data by assigning importance to different parts of the input to predict the next token in a sequence. These models win the imitation game by calculating the linguistic probability of a human-sounding response. They do not attach semantic meaning or lived experience to the words they generate. It is a functional realization of the Chinese room argument. A system can manipulate symbols according to a set of programmed rules without possessing any actual comprehension of what those symbols mean. Large language models did not evolve to think. They evolved to be the ultimate players of the imitation game. In his 1950 paper, Turing explicitly tried to counter a mathematical objection raised a century earlier by Lady Ada Lovelace. In 1842, Lovelace was analyzing the limits of early computing, specifically the designs of mathematician Charles Babbage. Babbage designed the analytical engine, a mechanical computer built from intricate brass gears. It was a deterministic machine, strictly following its mathematical rules. Lovelace observed a hard limitation in this design. She argued that the machine has no pretensions to originate anything. It can only do what we know how to order it to perform. Her 19th century critique accurately describes modern language models. They excel at generating statistically expected text, following the hidden orders of their training data, but they fail at true origination. Generating expected text works for conversational mimicry, but the system collapses when asked to synthesize entirely novel solutions to complex problems that do not exist in its dataset. This origination deficit is the boundary line. It separates a pattern-matching algorithm from true artificial general intelligence. To measure this deficit, nearly 1,000 global experts collaborated to build humanity's last exam. They designed 2,500 questions covering specialized fields, extending far beyond the standard academic curricula used to train current models. This image shows a block of ancient Palmyrene inscriptions. The exam requires the AI to parse specialized, context-heavy data exactly like this. Translating an ancient script or analyzing a bird's microanatomy requires deep expert synthesis. A machine cannot solve it by simply retrieving adjacent facts from its training data. The researchers built a filtering methodology. Every question was tested against top AI models. If solved, it was deleted. This strips away problems solvable by probabilistic matching. Only questions that defeated every AI model made it into the final exam. Humanity's last exam successfully neutralizes the pattern recognition advantage of the language model. It forces the machine to either exhibit true expert reasoning or fail completely. Turing's 1950 paper compared the mechanics of the mind to the skin of an onion. We can peel away the first outermost layer of apparent intelligence, conversational fluency, which we measured with the Turing test. Beneath that is the next layer, academic memorization, measured by benchmarks like the MMLU. Peeling that away reveals a dense core representing deep human expertise. Turing's premise was that as we strip away the explainable mechanical functions of the brain, we search for the real mind at the center. Modern AI architectures are currently trapped in the outer mechanical layers of this onion. They are currently unable to penetrate the core of specialized, contextual human expertise. When AI fails these new tests, a common counterargument is that researchers are moving the goalposts so the machines can never win. But high scores on older benchmarks like the MMLU simply measured how well an algorithm completed tasks optimized for human learners. They did not test for human experts. True cognition involves cross-domain synthesis, the ability to apply abstract principles to unique, non-repeating problems. These are specific logical operations that existing pattern recognition algorithms are not built to execute. The Turing test is now a historical artifact. It proved that machines can mimic human communication, but communication does not equal cognition. The goalposts haven't moved. Science has finally built a metric that measures the actual field of play, and that field reveals that true intelligence, depth, specialized context, and the synthesis of novel ideas remains uniquely human.